Friends, let us start discussion on the last topic of this course, and in this we are going to look at some non-ideal flow patterns or non-ideal flow of fluid in the reactors and its influence on the conversion, yield, selectivity and so on. Now, why is this non-ideal flow important, or what is it that we have not considered so far that this becomes an important discussion? If you recall, for majority of the discussion so far, we assumed our reactors to have ideal flow patterns, namely a complete mixing such as a stirred tank reactor or no mixing such as plug flow reactor. But as you can well imagine that reality will be somewhere in between, and here are few examples which may occur inside the reactor, so that we need to worry about how this reaction will proceed. To begin with, let's look at some of the typical flow patterns inside the reactor. For example, let us say that we have a stirred tank reactor, and that is something that we use quite frequently. So, we have a stirred tank reactor here, we have a stirred tank reactor over here, and the liquid is coming in from one side and is leaving from other side. Now, our idea that reactant is well mixed is essentially because of this impeller that we have in the reactor. So, this impeller is set at certain agitation speed, and that causes mixing by setting up the flow patterns such as shown over here. Now, ideal flow pattern or ideal mixing or ideal reactor is the one where we say that there is a complete homogeneity inside the reactor. So, if you look at the reactor contents in this zone, in this zone, in this zone or anywhere inside this reactor, the concentrations are uniform, and it is the same as what is coming out of the reactor. So, now let us look at what happens actually when you carry out these experiments. So, for example, it is likely that when some fluid comes inside the reactor, some of this fluid, instead of entering into the main reactor, actually just simply goes out of the reactor by bypassing almost entirely the reactor. That is one possibility. Other possibility is that some of the liquid comes to this region, which is corner of a reactor, and stays there for a long time, or sometimes what seems like forever, and therefore does not participate in whatever else is happening in the reactor. Or in other words, our assumption that all fluid elements on an average has spent residence time tau equal to volume divided by the volumetric flow rate is not necessarily a good assumption. Some of the fluids spends times much less than this residence time, such as the fluid which is bypassing. Some of the fluid stays much longer than this residence time, such as the fluid element which has got caught into this dead zone, and remaining fluid, depending upon when it gets time to escape the reactor, comes out at differing amount of, after spending differing amount of time. The same thing can be observed in a column reactor. For example, if you have a plate kind of reactor for gas liquid contactor, we have gas coming in from the bottom, we have liquid coming in from the top, and these two have to contact each other for reaction to take place. Now, depending upon the kind of flow, for example, there may be some fluid which just keeps recirculating in these zones over here, some fluid which just takes the shortest route and leaves. So, in other words, fluids spend times which are different than this average residence time in the reactor. The same thing can be said for trickle bed reactors or packed bed reactors and so on. So, the idea is that now if you look at this reactor, we say that this reactor is a confined a piece of equipment, or is a piece of equipment where our reaction is confined. We do not consider reactions in the inlet or after they have exited the reactor. But now if the fluid elements are not residing in this reactor for same amount of time, some are coming out quickly, some are coming out very late, or in other words, there is a distribution of the residence time as far as, or distribution of times as far as how long the fluid has spent in the reactor, the conversion in the reactor definitely is going to be significantly affected based on how these reactions take place. So, while talking about the real reactors and real performance of the reactor, we have to consider how is the distribution of these times that these fluid elements have spent in the reactor. Is it favorable, unfavorable and so on. We will see some of the examples and then look at its influence. But there is another aspect also which we have to consider. So, let us say that we have our reactor, and there is some fluid element coming in. So, now if you look at our reactor, we will find that there are fluid elements which have spent differing amount of time. Now, what is a fluid element? Fluid element is just nothing but a concept to say that the small volume of the reacting fluid is small, but is also large in some sense, that is large enough so that we can define the continuum properties of the fluid medium, for example, concentration and so on. So, our fluid element is not small such as it is at a molecular level, but there are lots of these molecules, so that we can describe the properties of this fluid element such as density, concentration by the continuum property, concentration such as kg moles per meter cube and so on. So, let us say that some fluid element has spent this has come inside the reactor, and after some time another fluid element comes in the reactor, it spends some time and so on. So, one aspect we just now saw is to see how long these fluid elements are there in this reactor. That is one of the important consideration for us. But apart from the fact that we have to consider how long they have spent, we also have to worry about how does these fluid elements interact with each other. That is, these fluid elements which have come at differing amount of time in the reactor are spending some time inside the reactor, do they mix with each other? Do they interact with each other, or do they just remain as an isolated entities, spend some amount of time and simply leave this reactor? Now, a gut feeling tells us that not only the time that they spend, but the quality of their interaction with each other will also make a difference as far as the reactor performance is concerned. And in other words, the mixing at a micro level, that is mixing at the fluid element level, is also of equal importance. What are, again, one can look at this phenomena as two extremes. It is always helpful to look at the limiting cases, so that the actual cases fall somewhere in between. One limiting case is complete segregation, where this fluid element 1 and 2 never interact with each other. So, fluid element 1 enters the reactor, let us say spends 5 minutes in the reactor, goes out. Fluid element 2 comes after 5 minutes, after the first one has entered, spends 7-8 minutes, whatever it takes, then leaves the reactor. So, there is no interaction between these fluid elements, and this is a situation of what we call complete segregation. The other extreme is maximum mixedness, that is, these fluid elements interact with each other as soon as they come into contact with each other. So, the fluid element which has come inside will mix with the other fluid elements and then leave the reactor. So, we have to worry about not only the residence time distribution, but the quality of mixing in the reactor, and this gives rise to idea of what we call micro mixing. A term often is used to describe the residence time behavior, and we call such term is used macro mixing. So, we have macro mixing and micro mixing, and then there are several other ideas which become important when we want to discuss the reactor performance for non-ideal flow behavior. So, let us try to now define few terms and try to understand how we can determine the behavior of fluid flow inside the reactor, how do we characterize it, and then later on we will come to the part where we try to use this characterization methods to describe the behavior of the reactor. So, we start our discussion on non-ideal flow patterns or non-ideal flow and reactor behavior by defining few quantities, and the first quantity we define is age of the fluid element. Again, fluid element a small volume, small in relative in relation to the size of the reactor, but large enough so that we can define the properties in a continuum domain such as concentration, density and so on. So, we define the age of the fluid element is as the amount of time the fluid element spends inside the reactor since its entry to the exit. Okay. So, that is what we call the age. So, once again, the age of the fluid element is the amount of time that has elapsed since the entry of that fluid element inside the reactor. Now, given this fluid element and this definition of age, let us try to define certain distribution that are used to characterize this fluid. And the first one we are going to define is what we call exit age distribution. Exit age distribution. So, as the name suggests, we are looking at what is happening in the exit of the reactor. Okay. And we said that different fluids spend different amount of time inside the reactor, and hence we know that there is a distribution of this age exit measured at the exit point in the reactor. So, what it simply means is, suppose this is my reactor, and I am introducing some fluid elements, and I am just, this is purely arbitrary. Suppose this is 1, then this has come sorry, I should followed by this is my reactor. So, let us say this fluid element is followed by 2, 3 and so on, 1, 2, 3 are sequential times, and needless to say that they are at some point of time they will come out of the reactor also, and therefore, if I place myself in this exit and calculate what is examine these fluid elements, and then define, we give a term E of t to denote exit age distribution, and E of t dt is nothing but the fraction of the fluid elements, that is the fraction of the fluid elements at exit. Okay. So, we are looking at what is happening at exit stream, which has age between time t and t plus dt. So, E of t dt is the fraction of the fluid elements in the exit stream, which has age between t and t plus dt. So, this is how I define my exit age distribution. Okay. We will take an example little later on, but first let us go through some of these definitions, so that we can look at the example all together. Now, given the fact that fluid elements, once they enter the reactor, they may spend differing amount of time, but eventually they all come out of the reactor. If that is the case, then if I look at this fraction, that is E of t dt, which we said is a fraction of fluid elements between age t and t plus dt, and if I add all these fractions from time t going from 0 to infinity, what does this mean? This means that I am looking at this fluid element in the exit stream and seeing what is its, how much, what fraction has spent time between t plus dt, and enumerate all this between time t equal to 0 to a very large time, let us say infinity. Then this all must add up to 1, or in a continuum domain integral E of t dt must be 1. And simply put, what it means is that if I introduce a fluid element inside the reactor, it may spend some different amounts of time, but eventually all of this come out of the reactor. So, it could have age anywhere between 0 to infinity or very large value, but if I add up all those they all must add up to 1, because all fluid elements which have entered has to come out of the reactor. Okay. So, this is my exit age distribution. Let me now define another distribution with the help of this exit age distribution. Now, this is what is called cumulative residence time distribution. Okay. Now, let us go back to our figure and let me. So, I have all these fluid elements. Now, suppose this has spent, so let me just call them as 1, 2, 3 and so on. Now, when I look at these fluid elements and let us say that I want to know what fraction of these fluid elements has age which is less than, let us say 3. So, I will count all the fractions which have 1, 2 and 3, or in other words, if I look at my exit age distribution E of t dt and I want to find out what is the fraction of this fluid stream which has age less than or equal to t time t, some time t, then I will add up or in the continual domain integrate all those times between time t equal to 0 to t equal to time t, and this will give me what I call cumulative residence time distribution, or which we denote by f of t. So, what is cumulative time distribution? Cumulative time residence time distribution, f of t is the fraction of the fluid element which has age less than t, time t, and as the integral suggests, it is a cumulative distribution. Okay. So, this is the second distribution that we have defined. In order to avoid the confusion between the time t and this integral notation, so let us call it as t prime. So, now if I take derivative of this df of t dt, by integration formulas we know that this is nothing but E of t. So, the relationship between the cumulative distribution and exit age distribution is clear from this particular notation. Now, there is yet another distribution which we need to define. Now, the very fact that we have now identified that fluids spend different amounts of time in the reactor leads to the fact that the quality of fluid inside the reactor is not same as the fluid which is coming out of the reactor in terms of the amounts of time or ages of these fluid fractions. They must be somehow related, but it is not necessary that these two are exactly same, or in other words, the age distribution, if you look at what is happening inside the reactor, need not be same as the distribution that we observe at the exit of the reactor. And this introduces yet another distribution, which is called internal age distribution. Internal age distribution I of t dt is nothing but the fraction of the fluid element inside the reactor which has age between t and t plus dt. So, that is my internal age distribution, and these are important, for example, in fluidized bed reactor where catalyst is, let us say, deactivating. So, the distribution of what is happening inside the reactor we will be of importance, because that is what will determine the reactor or how much reaction conversion has taken place and so on. So, how are these two quantities related, that is internal age distribution and exit age distribution. Okay. So, let us take an example. Let us say that I have a reactor, and this is filled with all fluid which is blue color, okay, just for sake of argument. So, for time less than the starting time, and therefore, we call times less than the starting time or t 0 or 0 to be simply put. So, suppose this is what is happening. Now, let us say that at time t equal to 0, we start putting in red fluid in this reactor. Okay. Start putting in red fluid in this reactor. What was there in this reactor? The inside fluid was all blue. I let us say start putting in this red color fluid. So, what will happen at some time greater than 0, that is at some time down the after the startup of this red fluid, what will happen? We are putting in red fluid, but now inside the reactor there will be some red fluid, okay, along with my original blue fluid, which will be also coming out. So, what will be coming out? We will have both red and blue fluids. So, let us try to see how this situation can be described. Okay. So, what I am going to do is I am going to take a balance on the red fluid, okay, balance on the red fluid, okay, at some time t, and I am going to say that the flow rate of this fluid is f prime. Okay. So, at time t, okay, the red material which has entered the reactor so between 0 to t up to time t, some red material has entered the reactor, and what has happened to this red fluid? This must be the red fluid which is inside the reactor plus the red fluid which has left the reactor, right, because this red fluid can go nowhere else. The fluid that has been introduced in the reactor either is found inside the reactor or it has already left the reactor through the exit stream. So, if I say my f prime f prime is my flow rate, so which is constant, then in time t how much of the red fluid have I sent in? If f prime is the rate, then f prime t is the volume of the fluid which I have introduced in my reactor. Now, what has happened to this fluid? If I say that of the fluid of the reactor volume V, if I of t dt is the fraction of the fluid having age residence or age between t and t plus dt, then up to time t the total fraction of the red fluid which is inside the reactor will be given by adding up all these fractions between time 0 to t, right. Okay. Now, how much of this fluid has left the reactor between the time dt, that will be given by, if f prime is the flow rate and we have our cumulative age distribution. So, the fluid elements which has left the reactor up to time t is the cumulative age distribution, right. So, if I differentiate this, I get f prime equal to V of I of t dt, sorry, not dt. So, if I differentiate this equation, what I get is V into I of t plus f prime into f of t. Okay, this should be f of t. Okay. So, in other words, we get f prime into 1 minus or okay, let us or 1 minus f of t equal to V by f prime of I of t. So, that is the relationship between my different residence time. And what is f of t? F of t I know is integral 0 to t e of t prime dt prime. Okay. So, now let us look at some of the definitions, some of the properties and so on. So, going back to our material or distributions that we have already seen, we say that exit age distribution E of t dt is nothing but the fraction of the material in the exit stream which has age between t plus dt and t plus dt. Cumulative age distribution f of t is the fraction of the material in the exit stream which with age less than t, and internal age distribution I of t dt is the fraction of the material within the vessel which has age between t and t plus dt. So, exit age and internal age, two different quantities, one looking at the exit stream, another one looking inside the reactor, but these two are not independent of each other, because fraction cumulative residence time distribution f of t is nothing but adding up all those fractions from time 0 to t. So, that is our relationship between the f of t and e of t, or alternatively expressed in this particular form. And we also just now saw that 1 minus f of t is v by f prime into I of t. So, thereby internal age distribution and exit age distribution and cumulative residence time distributions are all related to each other. We will come to how we get these distributions in just few minutes, but let us just continue this characterization of this residence time. And we have various, the moment we have distributions, we can characterize these distributions by looking at various moments of this distribution, the first moment, the second moment, and so on. So, mean residence time, for example, is nothing but t into e of t dt 0 to infinity divided by e of t prime dt prime, again limit between 0 to infinity, but this quantity we earlier saw is nothing but 1. So, this is my mean residence time, the first moment of the distribution. Variance, that is t minus t bar, that is mean residence time, the whole square e of t dt, gives me the distribution around this mean. And the skewness, this should read cube, t minus t bar cube e of t dt, that is the third moment, divided by sigma raised to 3 by 2, that is s cube. It tells us whether the fluid is coming out much before, that is skewness as the term indicate. For example, this is my mean residence time, we will see the example, but if my distribution is something like this, that is lot of fluid is coming much before, or whether it is coming much after the mean residence time, it tells me the skewness. So, let us take an example and look at how we characterize this, or what is meant by. So, let us say that on x axis we have time and on the y axis we have e of t, our distribution that we were looking at, and let us say that distribution is something like this. Okay. So, now if we want to, for example, look at the area under this curve between time t equal to 3 to t equal to 6. So, this area under the curve, or in other words integral e of t dt between 3 to 6, which numerically for this distribution has a value 0.51. So, what does it mean? It means that 51% of the fluid elements come out of the reactor between times t equal to 3 to 6. Whether it is minutes or seconds or hours is immaterial at this moment, that will depend on what this time scale is. So, E of t, again E of t dt is the fraction having age between t and t plus dt. So, if I sum up all those fractions between time 3 minutes to 6 minutes, which is what is done when we integrate, it tells us what fraction of the fluid element has residence times between 3 minutes and 6 minutes. Now, in the same example, this area under the curve between 0 to 3 minute shown in the green color. So, 0 to 3 E of t dt, which here is roughly 0.2. So, what does it tell us? It tells us that roughly 20% of the fluid element has residence time less than 3 minutes, because I have added all those fractions between the time limit 0 and 3. This is nothing but my f of 3, that is f of t. So, if I integrate between 0 to 3, I get a value of f of 3. So, on this plot I have time and f of t. So, at time t equal to 3 minutes, the value is 0.2, and then I can change this limit of 3 to 1, 2, 3, 4 and generate what we call the cumulative residence time distribution. Okay. We had just now seen the relationship between I of t and f of t, namely 1 minus f of t is v by f prime I of t. Now, what is v by f prime? So, if we take this distribution and do this integral 0 to infinity, that is the first moment of this distribution, and you know how to integrate numerically given this distribution, this works out to be 5.19. Okay. Let us say put some units minute in this particular. So, what does this tell us? This tells us that the reactor for which we have got this distribution time like this, the mean residence time or the average residence time is 5.19, and it turns out that is nothing but v by f prime. So, if we know or t bar is nothing but v by f prime. So, if we can experimentally calculate this distribution, then we can then calculate what is, if we can calculate the distribution, we know what is the mean residence time, and then any of this quantity v or f prime, if it is unknown, we can estimate that using this relationship. So, now let us try to find out how do we experimentally determine these residence time distributions, and for this we have to do experiments naturally. I mean, that is the whole idea, right. So, what kind of experiments can we do? We can, for example, introduce some tracer elements. So, let us say that this is my reactor, and need not be a stir tank reactor, can be a tubular reactor as well. So, as we saw in the previous case where we introduce red fluid or whatever, we can introduce a tracer at time t equal to 0 and then monitor the progress of this tracer at longer times or times since its entry, and then calculate what fraction has come in and what is the concentration and so on. So, that is how we can determine the residence time. We need one more piece of information, we will come to that in just a minute. But what kind of tracer can we introduce? There are so many. We can introduce a dye, we can introduce a salt solution, something which does not undergo any chemical transformation inside the reactor, or something which does not undergo a physical adsorption onto the material of the reactor. So, the idea here is that you introduce a perturbation, a tracer, which can be a dye or which can be a salt solution or something which changes the pH and so on and so forth, or introduction of acid, that is, such that this tracer does not undergo any chemical degradation or transformation in the reactor or does not get adsorbed onto the material of the reactor, because we want to trace this tracer, and if this tracer has disappeared for some reason such which I mentioned just few minutes back, then we have lost our purpose of tracing this, because there is one more factors than just the fluid movement inside the reactor, which will give us different kind of. So, what kind of tracers, in what manner can we introduce? We can introduce as a pulse or as a step input. Now, what is pulse and what is step input? So, first of all, let us say that we have this reactor, which is colored fluid red or colorless or whatever, and then as a one shot experiment we introduce a blue tracer at time t equal to 0, and then at longer times, and then I stop it. So, I have this reactor in which I have as a one shot introduce this blue material. So, there will be some blue material here, but later on I am not introducing any more, and I simply monitor for this blue material at longer times. So, this was only one shot and I go back to my whatever red or whatever was there. So, one shot pulse experiment, and step experiment is something which we saw earlier, that is I introduce change the color from blue to red or something like this, and keep it red for all times beyond my starting point. Now, when we do that, what do we do? Suppose we are looking at concentration of this tracer in the exit. So, we monitor the concentration of this tracer in the exit, okay, at longer times. Now, what do we expect will happen to this tracer? So, let's just look at. Pulse and step are the general tracers that we put in a pulse manner or in a step as a step input, but let us consider a more general scenario. Okay. Let us say that this is our some kind of a input. Okay. So, this is my input, which could be a function of time. So, I have time on this axis. Okay. And after some time, I mean the fluid starts coming out. So, let us say that exit concentration profile is something like this. Okay. I am looking at what is the concentration at time t. Okay. So, this is my C e of t, this is my C 0 or input. So, I want to see what is C e at time t, and let me take a specific example. Let us say that this time is some 15 minutes. Okay. Time is some 15 minutes. Okay. Now, what comes out at 15 minutes, for example, would be what was put in at time t minus t prime. T prime is some time, or in other words, what comes out at this 15 minutes is, let us say, what was put in at time t equal to 10, that means I am putting my t prime 5. So, what was put in at time t equal to 10 and which has the residence time, that fluid elements, all those fluid elements which had residence time of 5 minutes, or in other words, all the fluid element, I mean that is just one part, the fluid elements that I will see or the concentration that I will measure at time t equal to 15 will consist of what was put in the reactor 10 minutes at time t equal to 10 minutes and which has stayed in the reactor for 5 minutes, or what was put in the reactor at 1 minute and stayed in the reactor for 14 minutes, or what was put at 2 minutes and stayed in the reactor for 13, or in general what was put in the reactor at time t minus t prime and has stayed in the reactor for t prime, and what is that? That fraction is E of t prime dt prime, and if I add up all these fractions from 0 to t, this is what I will see comes out of my reactor at any given time. Once again, what I see, what comes out of the reactor at time t is what I have put in the reactor at time t minus some time t prime and which has stayed in the reactor for time t prime, or which comes out of the reactor after t prime. So, for example, for 15 minute case, the example which we saw, what comes out at 15 minutes is what material you put in at 1 minute and which comes out of the reactor after 14 minutes, plus what we have put in at 2 minutes and which comes out at 13, and so on and so forth up to 15th minute, or in other words, this integral 0 to t C naught of t minus t prime E of t prime dt is what gives us what comes out of the reactor. So, this is what gives us what comes out. Now, we will stop here, but in the next class or next session we will see how we use this information to find out this residence time distribution, and how do we use this residence time distribution to decide on what conversions we will get in our reactor. Thank you.